In physics, we're going to deal with something that's extremely important. The man himself was also extremely important, Newton. He also came up with gravitational formulas that we're going to be using. He's also the guy who developed calculus along with Friedrich Leibniz of Germany. This is a man beyond intelligence who came up with ideas that we now take for granted. The first one that we may or may not take for granted, but we use the term a lot, inertia. Newton's first law of motion is all about inertia. And inertia simply means that if a body starts to move, it's going to continue to move. It's going to continue to move until other forces work out to make it stop. Like if I were to roll a ball in a room, if there are no forces working on it, it would bounce back and forth, back and forth, back and forth, and never stop. In fact, it would keep accelerating while it's doing that, which would be really kind of cool. Get to the point where it's going so fast you can't even see it anymore. But unfortunately, there are other forces working on. We call them unbalanced forces. The unbalanced forces are the ones that eventually cause it to stop. And the biggest one is friction. And we're going to get into friction in this chapter towards the end of it. And all the mathematics involved, that there's a lot. But we're just going to get into the basics right now. So he said, once it starts moving, it's going to keep moving until something works on it, which he called unbalanced forces. Same thing with the body at rest. If your body is at rest, or appears to be at rest, now we're talking now about relative motion, that's a whole different story itself. But if somebody is sitting in a chair, and that person can stay sitting in the chair, unless some unbalanced force creates a motion like a shove, or a planet running into another planet, and then you flying into a wall. Anytime someone uses the word inertia, that's what he's talking about. Somebody once asked me, how do you keep going on doing what you're doing right now with all these things going on? And I simply said, inertia. So, the first and second laws of motion is the topic, though the first one is inertia. Make sure you watch the two videos I have attached with this before we get into the presentation. I want to talk about the first one, which is the NFL one. And the second one is a British Indian woman who is incredibly talented and smart. And I don't know how she breathes, because during the whole thing it looks like she never takes a breath once, and she talks fast. So you might want to pause the video a lot when she talks, but every word out of her mouth is just golden nuggets. So look through that. In fact, she'll be talking about all three laws in this video, where we talk about the first two laws, and then the next video will be the third law. So if you've not done that yet, please pause at this point and look at the other videos, okay? Now, in the first video, this is presented by the NFL, and I thought it was rather interesting. To me, somewhat clumsily discussed, because they didn't take into account all the unbalanced forces involved, but the point is made, and we're taken, that when a running back wants to run a touchdown, run for a touchdown, that person is going to be met by opposing forces called defensive backs. So the analogy is certainly there. So if there's no running back or defensive back in his way, the running back is going to score a touchdown fairly easily. But if there are running backs in the way, or defensive backs in the way, then the running back is going to have a very difficult time crossing the line. That's their way of showing inertia, which is good. The problem is, if there were no running backs, and this has happened from time to time, there are times when running backs, if there are no linebackers, there are times running backs will actually not score a touchdown. They'll trip over their own feet, or they'll get an injury and pull up and fall down. I mean, there's a number of possible ways in which that running back isn't going to score. So we have to keep that in mind as well. So the unbalanced forces will simply mean what is going to keep the motion from going any farther. Or if the running back catches the ball on a pass from the quarterback, turns and looks, hesitates just a second, and then gets creamed by a linebacker. He was motionless at the time until the linebacker decided that he really needed to go backwards and stated his case rather well, I thought. Anyway, so that's the point they're trying to make, and that's kind of the fallacies in it, but I hope that you understand what they're trying to tell you there. Now, let's take another scenario that was not brought up by the NFL, and that is throwing a ball in space. If you throw a ball in space, what's going to happen to that ball? Well, you got nothing working against it outside the person throwing the ball. So and let's just say also that there are no planets anywhere nearby that's going to have the gravitational effect on pointing towards it. The reason why when you're in space and there's no gravitational force on you is because all the other gravitational forces from planets or suns or stars or black holes are so far away they have absolutely no overpowering value over the others. They all equalize, which means that there is a pull on you that is non-existent, so we call that zero gravity. And so when you throw a ball, there's nothing working against the ball. So it's just going to keep going on and on and on. That's inertia. Okay? But if I roll it on the floor, it's going to slow down. Why? Again, like I said before, friction and gravity will have something to do with it, causing or helping the friction along. So, in fact, that ball, because I throw it, it's going to turn out it's going to be going faster and faster because of the second law of motion as described by Newton. And that is that the force is equal to the mass times the acceleration. So you take the mass times the acceleration, and that'll give you force. So here's an example. We have a 200-gram ball rolled at an initial acceleration of 1.25 meters per second squared. What is the force on that roll? Okay? So we got F equals ma. And we got a 200-gram ball. That's the mass. And the acceleration is 1.25 meters per second squared. Now, it turns out that when Newton defined his force formula, he wanted the mass to be in kilograms. So we've got to convert the grams to kilograms. So put grams on the bottom, kilograms on top. Kilograms is a larger label, put a 1 there, and the number associated with kilo and kilogram is 1,000. So this is going to give us 0.200 kilograms. And so, according to this formula, then, the force, the measured force for this, is going to be 0.200 kilograms times 1.25 meters per second squared. Punch that out in your calculators, and you should get 0.250 kilogram meters per second squared. Now, and that's pretty much how Newton left it. Since then, we've decided to condense that label down from kilogram meters per second squared to a unit named after Newton, which we cleverly called newtons. So they define 1 Newton, which is just a capital N, as being equal to 1 kilogram meter per second squared. Therefore, the answer to this problem is 0.250 or 0.250, same thing, newtons. And that would be our answer. Now that's the initial force. And that simply means that if it's being rolled on a surface, that force is going to decrease because if the acceleration is going to decrease to the point where it becomes 0. It's going to stop moving. Alright? So now we go on to the second one, which is a 350-gram ball gets pushed with a force of 0.125 newtons. What is its initial velocity? Okay? So we have 350 grams and 0.125 newtons of force. $350-gram ball and 0.125 newtons of force. That's our force. That's our mass. And the question is, what is the acceleration? So using F equals ma, plugging in garbage. Well, we can't plug in all the garbage yet because mass has to be in kilograms. So we multiply this by 1 kilogram over 1,000 grams. And we get 0.350 kilograms. So we put 0.125 newtons for the force equals the mass, 0.350 kilograms times the acceleration. So we'll find the acceleration, take 0.125 newtons and divide by 0.350 kilograms. And our answer, which is calculated on the script there, is 0.357 meters per second squared. So, your practice problems related to this out of the book, page 135, problems 12 through 18. Good luck.